Lesson 4, scaled relationships. So we're going to look at the relationships between scaled copies. Today's I cans. When I see a figure and its scaled copy, I can explain what is true about corresponding distances and corresponding angles. I can use corresponding distances and corresponding angles to tell whether one figure is a scaled copy of another. So make sure you have today's date, your I cans, and your page number, and you are ready to move on. So just like the other lessons in this, you'll see that with this, there's a link for you to follow to go through and interact with these. You can open up that on the tab and kind of click back and forth. First thing is, I want you to take a look at these 3 shapes, and you should see these in that link. What's going on with them? Well, from what I see, at the very least, we can say that they do have at least some similarities to them, right? We have, it looks like a vaguely similar shape. They're all quadrilaterals, right? They're all 4-sided figures. It does appear that this line here, the AB segment, EF and IJ, what might be corresponding because they all seem to be the longest parts of them. It does appear that the angles are similar, but without measuring any of this, it's really kind of difficult for us to actually see any of that. But just by what we can see right now, it does seem like that these would all be scaled copies. So while they appear the same, it's really kind of hard to tell for sure if they are until we get something like a protractor. If all of the angles are the same, then they should be scaled copies. So go ahead and test it out for yourself. Okay, so I'm going to use that extend feature, and I'm going to measure a few of these angles. So I'm going to put that right there. And so it looks like angle DAB is, 60 degrees? Let's see if HEF is 60 degrees as well. Yeah, it looks like it's 60 degrees as well. And there we go. Yeah, it looks like LIJ, so at least this bottom angle in all of them is equal. What about this angle here, ADC? Looks like we have, 125 degrees on that angle. Again, it looks like 125. And again, it looks like 125. So far, it looks like that these are all congruent. And really, it's just a matter, when you're talking about these, it's a matter of turning it so that you can measure those angles easily. All right, I'm going to go. Let's see here. All right. Well, I'm having trouble here. Let me see. Oh, there we go. Okay. Let's see. Angle DCB is what? 80 something. Looks like 88 degrees. Looks like that. HGF, that's the corresponding one. And again, with each of these, I'm just checking on the corresponding angles to see if they match. And if they do, then I'm good to go. It's a little hard to tell on that one because of where it's turned, but it does appear so. All right, let me try this final one. Okay. Looks like that is a right angle. And that looks like it's a right angle. Now, it may be slightly off from what I'm using just because of moving everything. But just by the angles alone, we can see how they are congruent, or how they're scaled copies of each other. Go back here real quick. So the corresponding angles in all of these scaled polygons are equal, which means that every one of these, while not the same size, do represent the same picture, just in different sizes altogether. All right, so what about the lengths on all of these? We know the angles are all the same, which means that it should be a scaled copy, but how do we know about the lengths? Well, we talked about before about the distances across and the height of it. If that's the same as, if those are scaled as well, then all of our pieces should be the same. Because if our scale, or our line across here, our horizontal and our vertical line, both use the same scaling to make each of the other figures, goes to reason that these outside lines would be equal as well. So if we talk about something like dB equaling 4, so 4 units across, and from A to C is 6 units across, as long as we're scaling the same, it all works out. And we can see that we are in shape EFGH, we're scaling these the same way. Because look, what's happening here is, how do you go from 4 to 6? Well, you can actually multiply 4 by 1 and 1/2 to make 6, right? Because 1 times 4 is 4. 1/2 times 4 is 2. 2 and 4 make 6. Is 6 times 1 and 1/2 make 9? Yeah, because 6 times 1 is 6. 6 times 1/2 is 3, making 9. And you can see that going to IJKL, the smaller shape, that those same distances are used again, but this time we're dividing them in half, so it's actually smaller. So the horizontal in the polygons are using the same ratio as all of the others. It's still that same build. In fact, you could look at the 2:3 ratio here as being kind of that basic unit ratio in this situation. And the vertical, it's the same sort of thing, right? With all these ones that are on the vertical part here, it's the same sort of thing. And it's just something making each of the shapes the same because they're scaling by the same part. So from ABCD to EFGH, we're scaling by multiplying by 1 and 1/2. When you go from ABCD to IJKL, you're actually multiplying by 1/2 or dividing by 2. So we have that scale factor being used in each of those situations. What's the scale factor in this situation? Well, how can you multiply 6 by something to get you 15? Or how can you go from 15 to 6? Yeah, you could divide and look at 15 divided by 6. Or, if you're going from here to here, you're trying to find out what it is that you multiplied that 6 by to make the 15. Anyway, actually, it looks like we can divide a 3 out of both of those. which would get you 5/2, which is the same as 2 1/2. So if we knew the lengths of these other parts, we could scale them up the same way. We just have to multiply by 2 1/2 on this. So after you scroll down from those, there are 2 parts with that W. We did kind of one of them, so you can skip the second part on that. When you talk about 2 quadrilaterals here, we've got 2 that May says that ZSCH is a scaled copy of XJYN, but Noah disagrees. Why? Why not? Are they? Well, here's what I can see. If I measure that distance across there, I've got 1, 2, 3, 4, 5, 6. And I go from the top here. So I had 6 here. And I got 1, 2, 3, 4, 5, 6, 7, 8, 9 here. Now, if this is truly a scaled copy, then when I look at the vertical and the horizontal, I should be able to multiply whatever I do for the horizontal, whatever I scale factor it by, I should be able to use that same scale factor on the vertical, right? Because then that should be the same. So the horizontal is 1, 2, 3, 4. And the vertical is 1, 2, 3, 4, 5, 6. All right. So, does it work out? Well, I got 4 across here. Can you multiply 4 by something to make 6? Yeah, 1 1/2. If I multiply 6 by 1 1/2, will that make 9? Yeah, so actually we can tell right away that these actually are scaled copies. We can see that they have similar angles, but it's not necessarily going to be very easy to tell right away. So just because we've got the vertical and the horizontal numbers across being scaled, does that mean that this is? Let's look at one thing here real quick. Let's see if, we can't really measure the angles to prove whether it is or not, but we can do a couple things. Because look, if I look at this angle here with the N and the point where those two cross and the Y, that's a right angle, isn't it? Okay, so if this is true, then this triangle here should be a scaled copy of this triangle. Well, I've got 1, 2, 3, 4. I've got 1, 2, 3. All right, well, I could probably multiply by something to get that the same. But look at the vertical. I only have 1 here. This is 1 as well. Now, unless I'm multiplying both the parts by 1, then this angle here and this angle here are different than these angles. Look here on the other side. With the X, the N, and that point of crossing over again. We got a right angle in both of them. But then this angle would have to match this angle, and this angle would have to match this angle. So do the angles match? No. So, while one part of it looks like it's scaling, and in fact we can prove mathematically that those are scalable numbers, the rest of the shape hasn't been moved correctly to have the same thing, because we should always have the same angles, the same angle measurements. And when we cut these up in the same way, we should make the same triangles with the same different lengths, but with the same angles inside. So does the scale factor affect other measurements other than the segment length? The scale factor should just affect those lengths. It should not affect the angles. So not only can we, to make sure that we've got a scaled copy, should we be checking to see if those exterior lengths are the same or using an interior length that we can measure more easily. But we also need to check those angles to see if they are the same as well. Okay. So when a scaled copy is created, we know that the distance between any 2 points are scaled by the same factor, and the corresponding angles in the original finger, I guess you could have a finger there. I hope you're not cutting off fingers to scale copies with them. The corresponding angles in the original figure and scale copies are congruent. They should be equal. Okay, well, I think that's it. We should be good. Thanks for watching.